All right, so we just solved this very long initial value problem. And what we're going to do is we're going to work on one more example, but I went ahead and did the algebra for the fraction and all that ahead of time. So we're going to skip those details in this example and mostly just focus on the setup of the Laplace transform problem, so that hopefully we can keep this one really short. Okay, so that's our initial value problem. Y double prime minus 3y prime plus 2y equal to e to the minus 4t, with y of 0 equals 1 and y prime of 0 equal to 5. This problem you could have solved with methods from exam 2. It's a constant coefficient problem with a non-homogeneous part, but we're going to solve it with Laplace transforms. So what we're going to do is we're going to take the Laplace transform of both sides. We're going to say L of y double prime minus 3y prime plus 2y is our first concern. And that's going to give us 3 parts. Oh, I'll do this meticulously one more time. So linearity is going to give us L of y double prime minus 3 L of y plus 2, L of y prime plus 2 L of y. That's linearity right there. And then that's going to break up into 3 parts, where the last one, L of y, just becomes capital Y. And then if I'm taking L of y prime, that's the first derivative, so I'll have s to the power 1 times something minus something. And then the way I fill that in is the highest power s is always multiplied by y, and then I just start subtracting my initial conditions until I run out of space. So I subtracted y of 0, my first initial condition, and then all my spots were filled, so I stop. For L of y double prime, that's a second order derivative, so it starts with s squared minus s minus something. Following the same pattern, it's s squared, the highest power, times y, and then I just start filling in my initial conditions until I run out of space. And that time I used my second initial condition, y prime of 0, because I had to fill in the s and the 1 terms. So then if I go ahead and think, eventually I'm going to be solving for capital Y, so it helps to have everything that's attached to a capital Y together. So that's s squared minus 3s plus 2 times y, from that s squared minus 3s plus 2, those terms right there. And then all that's left over is minus s times y of 0 minus y prime of 0 plus 3y of 0 from this term, and that term right there. And when I plug in my initial conditions, that's minus s times 1 minus 5 is y prime of 0 plus 3 times 1. So that's just going to be s squared minus 2s plus 2 times y minus s minus 2. And then I have to take the Laplace transform of the other side, L of e to the minus 4t. And that one we don't have to do anything special to. We can look at our Laplace transform table and see that that's 1 over s minus a, for a equal to negative 4. So that's just 1 over s plus 4. And so when we set both sides equal, we can see that our differential equation is equivalent to s squared minus 2s plus 2 times y minus s minus 2 equal to 1 over s plus 4. That's an algebraic equation that has only s's and capital Y's. All of our little y's, derivatives of little y, and t's disappeared when we took the Laplace transforms. And if we wanted to solve for y, Actually, I'll go ahead and just write that on the next slide because I would rewrite it anyhow. If we solve for y, what we would have is y equal to s plus 2 over s squared minus 3s plus 2 plus, let's see, 1 over s squared minus 3s plus 2 times s plus 4. Yep, okay. So all I did was I isolated my capital Y. Again, this is that thing that changes for every problem. It's whatever big Y is equal to. And then I'm going to go ahead and write in right here the partial fraction decomposition that turns this into something that we can take the inverse Laplace transform of. So this becomes minus 16 over 5 over s plus 4 plus 25 over 6 over s minus 2 plus 1 over 30 over s minus 1. And that would be similar to that very long partial fraction decomposition part I did of the last example right here. But once you did that very long algebra problem, you could take the inverse of both sides. So we've got L inverse of big Y is equal to L inverse of minus 16 over 5 over s plus 4 plus 25 over 6 over s minus 2 plus 1 over 30 over s minus 1. And linear, well actually, the left side is just going to be little y of t. And then linearity tells us that this is minus 16 over 5, L inverse of 1 over s plus 4, plus 25 over 6, L inverse of 1 over s minus 2, plus 1 over 30, L inverse of 1 over s minus 1. Linearity. And then all of these are just exponential type terms. I've got an a equals minus 4 to get s plus 4. I've got an a equals 2 to get an s minus a is s minus 2. And an a equals 1 to get an s minus a is an s minus 1. So then our inverse Laplace transform table would tell us that that's minus 16 over 5 e to the minus 4t plus 25 over 6 e to the 2t plus 1 over 30 e to the t. That would be, oh no, I'm always overzealous with that box. Okay, I'm just going to underline it. That would be our solution. And then if you go ahead and look back at our differential equation, there is an e to the minus 4t on the right-hand side. During exam 2, you would have solved this with undetermined coefficients, yp equals a times e to the minus 4t. That appeared right here. And on the left-hand side, the homogeneous part would give you an auxiliary equation, m squared minus 3m plus 2. But that's just m minus 2 times m minus 1. So m equals 2, m equals 1. That would give you e to the 2t, e to the t. You're seeing that e to the 2t, e to the t right there. So hopefully that confirms that we did this correctly, or at least gives you a feeling that we did it correctly. So that example is the last thing that I have time for. We'll do a wrap up real quick.